Good day, everyone. Today I'm going to speak with you about a new substitution and elimination reactions. So this is really a matter of converting poor leaving groups into better leaving groups, uh, making better nucleophiles out of lesser likely or lesser thought of sources like CH. So, for instance, if you have something that's electronegative that's pulling electron density away from a hydrogen, it can become more acidic, and then you can form something that can make a strong carbon-carbon bond, single carbon-carbon bond. Okay, well, first let's start off with converting this OH group to a good leaving group, or much better leaving group, because this is actually a poor leaving group. Now, notice that OH is going to be attacking this Lewis acid here, this PCl3. PCl3 is going to have a full octet. The lone pair is not shown here, but nonetheless, this chloro group will leave, and it'll be a substitution. Now, you will form a charged species. It's not really going to change the stereochemistry on the left side. On the right side, you're going to see that once you now have a good leaving group, so much of a good leaving group that a Cl minus that is left is now going to act as a nuke to remove this POCl2H species. So chloro with its full octet, it's going to attack at that carbon opposite, right? So going in from behind the page into that carbon and removing this good leaving group. Okay, so you can think of this almost like a protonated form of this, where water is going to be a good leaving group if it's OH2 plus. Okay, so it's just analogous. You could just think of this as a hydrogen here. Okay, so now that we have that substitution, we see that we have an inverted stereochemistry, so that should indicate that it's an SN2 reaction. And of course, on the side, you have your leaving group that's just now a neutral species and more stable. Okay, so this works for primary and secondary alcohols consistent with bimolecular SN2 reactions, so SN2 bimolecular substitutions. All right, so a nucleophile that was out of control. This is referring to primary amines in the presence of strong electrophiles. So in this case, sort of the textbook example for a strong electrophile is ethyl chloride. So remember that this chloro group is pulling electron density away from that carbon. You have an amine that has a lone pair and will coordinate to that partial positive carbon that is electrophilic. Henceforth, you're going to have this happen about 3 times. And just to show you the first product, at least the intermediate, you're going to have a charged species once again. So you're inducing some kind of charge separation from the Cl minus leaving, and then this NH2 or amine attacking the ethyl group aggressively. Okay. Now, a second equivalent of amine will come around and act as a weak base to remove that. It's going to be more acidic. Okay, and then you'll have now a secondary amine. Okay, and then if that is introduced into another equivalent, it's not a very controllable reaction, so this typically ends up in a distillation setup, which some of you know is kind of messy, and it's even more so messy when you have an amine mixture. I've been in, commercial plants where they have that in, very, very large quantities, and it is nice to be around. I mean, ammonia by itself is pretty bad, but this stuff is pretty nasty. So, nonetheless, this is going to just continue to attack ethyl chloride species continuously, and eventually you get to the point where you have, disubstituted, trisubstituted, even tetrasubstituted species. So this just kind of continues on until you get into a quaternary species of amine. Now, also, let's just think about a conceptual check here. What happens when more alkyl groups are attached to the amine's nitrogen? Well, that just means that there's going to be more electron density is going to be fed in from those ethyl groups, or alkyl group or alkyl chains that are directly attached to that nitrogen. So that'll stabilize a positive charge. So, in other words, that nitrogen will be still fairly acidic in its conjugate acid form, as well as serving as a moderate base. Okay, but again, if you were just looking to monoalkylate in this particular instance, it's going to be hard to control. Okay, because again, you're just feeding more electron density into that nitrogen. Okay, moving on. That'll come back towards the end of the lecture here. Let's talk about bimolecular substitutions with relation to thermodynamic versus kinetic enolates. So you've heard of pretty much the conjugate acid of enolates, which are enol and ketoenol tautomerism. Just again, the conjugate base form here. So in other words, it's going to be a hybrid, a resonance hybrid that is going to be, of course, delocalized between an oxygen and a carbon in sort of this shift pi bond structure, filling up different orbitals. So therefore, that negative charge can kind of lend out electrons to a formidable electrophile, just like what we have right here. Okay, so here's the substrate. So generating a keto or enol tautomer or enolate as it is in this case, you have to actually deprotonate an alpha carbon with respect to a carbon-oxygen double bond. Okay, so you have two ways of going about it. Here are the two bases here. So this is what is commonly referred to as LDA. LDA is lithium diisopropylamine. It's very bulky, and it has a very high conjugate or high pKa for its conjugate acid form. So in other words, this is very basic as an anion. And then you have potassium terbutoxide, which has a lower pKa, somewhere in the neighborhood of 17, 18, 19-ish, somewhere in that neighborhood. So in other words, it's going to be not as strong, but you would use this for a different application. Okay, so if you were trying to, let's say, remove a hydrogen selectively from, let's say, an alpha carbon that's already branched in two other positions. Okay, so you're going to need something that's a little bit more accessible, like a terp butoxide. This is going to be too large to try to interact and take that hydrogen away. So in other words, it's going to take the most accessible site the fastest. Therefore, this is what is referred to as a kinetic enolate. Okay, so something that you can use at low temperature. Typically, you're going to use a CO2 and acetone bath to get things nice and cold, and gradually kind of warm things up over time to say 25 degrees, and you'll have already added your electrophile, etc. So this is going to be under kinetic control, low temperature. Conversely, as you might have guessed it, under thermodynamic control, potassium terbutoxide is going to take this hydrogen to form the more thermodynamically stable enolate as a result. So what that looks like for here, we're really going to have, draw this without the hydrogens now, so kind of okay, so remember that this lone pair can resonate back and boot up these electrons. If you can't see that really well, but okay, so here's the enolate form, this is the keto form. Okay, so this resonance hybrid between this enolate and then this keto form that's in anion. Okay, so as they sway back and forth, this is going to be the most unstable. So therefore, it's going to lend its electrons out to some kind of electrophilic species right here. So okay. So therefore, you're going to have that substitution at this alpha carbon, not this alpha carbon. The kinetic product is where the substitution is going to occur right here at the most accessible point. Okay, so what you're going to form is a product here. Again, under thermodynamic control. Is this? Okay, so just so we're clear, this is going to be an ethyl group. Sorry, it's kind of dragging over towards that line. I didn't save myself enough space. My bad. All right, so what the substitution is going to look like over here is the LDA is going to remove this hydrogen here. So let's pull this guy way down. And whoop. Okay, so it's going to pluck that proton off. And then your nuke's going to be over here. So really didn't give myself enough space. Anyway, nonetheless, this is a ketone. I know that definitely does not look like a ketone. Sorry, it's been a long day. Okay, so we have the ethyl group right over here, alpha to this top ketone. This side isn't accessible because there's no hydrogen there. You just have two methyl groups branching off that carbon from the ring. Okay, so, and this is a methyl, just FYI, just from this. Okay, so really you have to think about what kind of stereochemistry you're going to get here. Now, you can actually have this going into the plane of the page, or let's say in this example we'll go out, and then I'll give myself enough room up top right here. Okay, and then the other one is going to go into the plane of the page. Okay. All right. So in other words, you should pay attention to the R and S. So this should be a racemic mixture. Okay. So let's look at alpha carbon halogenation, different results under acidic and basic conditions. So I'll start the reactions off for you here. They're already kind of drawn out. So we have this protic hydrogen that's, again, alpha to the, what is it? To the carbonyl, sorry. And then we have an electrophile that's formed here. Think of this bromo group that is attached to an ethyl group like above. Now, the difference is that this is going to have an instantaneous dipole, not a net dipole like what you see over here. All right. So once this is kind of partial positive just by a sway of, probability of electrons being greater on one side than the other, that's when that enolate will attack, and there's going to be a bromo leaving group to take its electrons with it. Okay, so your product that you'd form here. And that would continue, because remember that if you have a bromo group or some kind of halide directly there at the alpha carbon, this hydrogen right here is going to be more acidic. Okay, so not only are you having an electronegative group here tugging electron density away, you're also going to have that from the carbonyl as well as this electron withdrawing phenyl group. Okay, so, but more so from this weirdo looking CO double bond. All right, so this will continue. Not so much for the acid condition alpha bromination here. So this is usually on an alpha carbon to a ketone. So, you can have an additional branching site over this way, right? Really the most acidic hydrogen is going to be right next to the CO double bond. All right, so once this hydrogen is plucked off, then you have this leaving group here, right? So H3O can really act as a good electrophile in a sense. So now that that positive charge is picked up from that hydrogen, and it's dumped off in that proton transfer, now this particular oxygen is going to have the ability to pull electron density away from this carbon. Okay, and as such, it's going to further activate this carbon to where an electrophile can attack it. Now, in this case, there's going to be some kind of resonance, because this hydrogen right here is going to be even more acidic as well. Now, water is going to behave as a base to remove that proton there. And, and then you have this electron push up this way. Okay, now, once these lone pair of electrons come back down to reestablish that pi bond, it's going to kick this pi bond out to attack that Br2, right? And again, one side being partial positive and the other side being partial negative just from the electron shift. Okay. All right, so what you're going to form there is just write pH for short. All right, and then that monobromination is going to occur. So why couldn't an additional alpha bromination occur? Well, because you're just already tied up with that positive charge about that oxygen, so you can't really dump off another hydrogen there. And if you already have that catalytic hydrogen around as H3O from this original previous step, then you really don't have any way to pluck off this hydrogen, which is way more acidic than this hydrogen. So you're kind of stuck in a rut there. Therefore, you're only going to have one bromination or chlorination or whatever, even iodination at that particular alpha carbon, just at that just that one substitution, just that monobromination. Okay, so it's pretty much locked up there. You can't go any further. Okay, so that's the difference between doing things under acidic conditions versus basic conditions. Okay, so let's get into this irreversible reaction involving diazomethane, which is actually quite reactive. And in fact, it's definitely sort of an explosion hazard, if you will. It's definitely not something to play around with. So it behaves both as a base and a nucleophile, particularly with carboxylic acids. So diazomethane can actually form other species that we'll get into later in the book. But this forms a methyl ester irreversibly. Okay, so irreversible how? Well, we'll see. Okay, so the first step here is, like I said, diazomethane acts as a base. So it's this Vitter ion. You know, some electrons can shuffle around, but it's going to be net neutral as a species. So you'll see it as CH2N2, you know, under a reaction arrow or what have you. Now, this basic carbon is going to pluck off that hydrogen like, you know, hot item, and like toilet paper these days, yeah. And then oxygen, electrons are going to go back to oxygen, form a negative charge, conjugate base, and that's going to behave as an attacking group to that now CH3, which has a great leaving group, right? So if this diazo group leaves, it's going to behave as a great leaving group because it's going to become N2, which is highly stable and abundant in the atmosphere. So then you essentially just form your ester group and you're good to go. Okay, so this happens in very good yield. Not this semester, but next semester you'll start to look at reversible ester formation involving, you know, either H2SO4 or some kind of acidic conditions to merge an alcohol with a carboxylic acid. So, but we won't get into that today. Let's look at ether and epoxide or cyclic ether formation. First off, we're going to talk about just simple ethers or linear ethers, if you will. Williamson ether synthesis involves an alkoxide anion, so that means a conjugate base of an alcohol, and a primary or secondary electrophile, which would be an alkyl halide. Surprise, surprise. So this is going to act as a good nuke. Even though you think of this as pretty bulky, remember that this is going to be primary, so therefore it's going to be highly reactive and accessible. So with that, you're going to have an elimination, or sorry, a substitution rather. And that Cl minus is going to leave. And then you have your asymmetric ether right there. So really, Williamson ether synthesis is the best way to synthesize selectively a certain type of asymmetric ether based on what you know, preference you have on either side of that oxygen. So it's just a matter of figuring out what's the better electrophile, what's the better nuke. Okay, so let's look at other symmetric ethers. So the most effective way is to just use H2SO4. I kind of alluded to that with forming esters, but in this case we're going to be forming ethers that are different. So we're just going to take, you know, some di or tri-substituted alcohol, and take two equivalents of those and just condense them into sort of that Star Wars fleet-looking deal over here. This di-isopropyl ether, I guess. And then we have water as a byproduct, right? So again, this acts as a base. So it's going to pluck off one of these hydrogens here, or have it transferred to it, whatever way you want to look at it. And it's going to behave as a moderately good leaving group. And then another equivalent is going to attack that carbocation. Okay, so now asymmetric, or we also see that for tertiary alcohols to condense together. Now, asymmetric needs the alkoxide anion slash alkyl halide approach or combination, like I said previously with Williamson ether synthesis. All right, so after talking about this for so long and on a 25-minute streak, I'll give you guys the floor. Give yourself a minute to work out this particular synthesis. Look at problem 10.48 on page 559, and give yourself about 5 minutes and try to work everything out with the mechanism and all, and then we'll go over. All right, so this OH group is going to act as a weak base to pick up that hydrogen away from the acid. Okay, so then we're going to form that intermediate, charged intermediate. So this is going to leave. Again, this is a poor leaving group on by itself without being protonated. So once it's left, it forms a carbocation. You have water that goes. All right. And now, remember, you're going to have a dipole going in the direction of that oxygen. So that oxygen is going to be most electron rich. Coordinate there. Pending formal charge right there with the intermediate, a protonated ether. And then an additional hydroxyl is going to come around, either being that cyclopentanol or the 3-propanol, and remove that hydrogen. Then you're going to get your stable neutral species. Okay, same thing as we have up here. So you can see, you can just envision a condensation here with 2 cyclopropanols. Same goes with 2 equivalents of 3 pentanol. Sorry, not cyclopropanol, cyclopentanol. So pentanol, 3 pentanol, cyclopentanol. Just for the record. All right. So let's look at forming epoxides now. So epoxides are essentially just 3-membered rings. As you can recall, they're fairly strained just from that electron overlap. And oxygen's looking to tug electrons away from those 2 carbons. Okay, so both of those carbons are actually going to be rather reactive, especially depending on what conditions there are, what kind of substituents are hanging off of them. But let's look at intramolecular Williamson ether synthesis. So this is problem 10.50 on page 559. So you have a strong base like NaOH, which is going to remove that hydroxyl hydrogen, it being slightly acidic, especially since bromine is going to be pulling some of that electron density downward. Okay, now that alkoxide that's alpha to where the bromine is connected is going to do cyclization and attack this electrophilic carbon, booting off that bromo group. So Br minus leaves. Okay, so it's an intramolecular Williamson ether synthesis. You see that with some 6-membered rings, some 5-membered rings as well. Just depends on the species, right? So typically 5- and 6-membered rings are more abundant within nature. Okay, so let's look at epoxide ring reactivity. Is the role of electrophile. So especially under acidic conditions, because these lone pair can still act as electrons that will coordinate to a H+. So this is coming off H3O. Okay, and then we have this intermediate here Okay, so it's what this positive charge is going to do is tug electron density away from the more substituted carbon that has some electrons that feed in, right? So this one doesn't have much, just with the 2 hydrogens there. So in other words, this site is going to be more reactive. Let's say if you have this methanol, which is going to be a weak nuke, it's going to come in. It shouldn't matter too much because those electrons are going to go up to that oxygen. And then you're going to form this methoxy hydrogen group. Okay, so or methoxy here and hydroxyl here. And something similar is going to happen with things in the basic medium, but the reactivity is going to be different in terms of regiochemistry. So it's actually going to boot off the sigma bond to form this alkoxide. Right. And then this is going to be strongly basic, so it's going to pick up some hydrogen, say from another methanol group. So another proton source. We get our product. So now the hydroxyl is still about where those 2 methyl groups are branching off, and then you have the ether opposite of it, of the other carbon. So then we're also going to have OCH3 conserved. So that negative charge is back on the next OCH3, and so it goes to the next one. Okay. All right, so let's look at 3 examples here. I'll pause for a little bit, give you a minute to catch your breath, and get started on these. So let's just take a look at our options here. KCN, that cyano group is going to behave as a good nucleophile, but in order for it to be KCN as a conjugate base of HCN, it's going to need some kind of basic environment. So with the basic system, you're going to get the attack at the least substituted carbon on the epoxide, and then vice versa when you're talking about the under acidic conditions. But neither of these are under acidic conditions, at least not initially. So KCN is going to be basic. Lithium aluminum hydride, which is a strong reducing agent, or hydride. So hydride content is going to be what's attacking either of these carbons. I'm not going to give it away. And then this CH3Li, that's going to be a strong nuke as well. So see what kind of products you come up with for that, and then we'll go over it together. So pause and give it a couple minutes. All right, so let's say this negative charge cyano group attacks here. It's going to attack the least substituted carbon. It's going to push these electrons up. Now remember that these epoxides do have sp3 hybridized carbons, so you do have to take care and take consideration of chemistry, or stereochemistry rather. All right, and this ethylene glycol will actually behave as an acid in this particular case. So a proton source. Okay, so it's going to be a higher boiling solvent if that were to be its another form of use. So protic. All right. That's typically what's in antifreeze, ethylene glycol, or at least what used to be. It's teratogen. Okay, so really the best way to keep the stereochemistry straight is to keep everything in the same plane here. So from the beginning, that CN minus attacked right this carbon that's about the plane and pushes these three bonds that are all, again, flat on the plane of the page. Okay, so same thing you're going to see here. So lithium aluminum hydride is going to look like this. So lithium plus, and then aluminum is going to be the center element about. Okay, so aluminum is going to have a formal negative charge. So that means one of these hydrogens is going to act as a nuke. Okay, so it's effectively like an H minus, if you will. So you just think of it as H minus. Not the same as NaH, because NaH is a good base. This is acting as a better nucleophile. Okay, so again, it's going to break up that bond. Remember that this three-member ring is going to be very strained, so that bond is just looking to pop open. Okay, and then we have alkoxide anion, and notice that the second step is when they actually introduce H3O. So that 1 and 2 that you see right there, those are physical separations and or changes in basic to acidic environment. So if you were to add H3O to lithium aluminum hydride, you're just going to be willfully adding that hydrogen plus to a hydrogen minus effectively, and rendering it inactive. So you have to have two different steps. Okay, so this hydrogen would just be attached to this methyl group, which would, for all intents and purposes, would not be stereospecific, right? It's just going to be a methyl group. So and this is on to the second step with H3O. Okay, so you're going to form water. Really, you're just going to form that. All right. Last one. I'm just going to draw the product. You can kind of guess what's going on from here. So those are almost in the same plane like you would think of, say, a good E2 substrate, right? But instead of having a hydrogen, you have a CH3 group. Okay, moving on, next couple things to round out the chapter 10. Alkyne formation, so eliminating dihalides with concentrated base and high heat. So remember that under high heat and high base concentration, you're going to force some kind of an elimination reaction, whether it be unimolecular or bimolecular. Depends on how there's a rotation and if there's that alpha carbon that's accessible. Now, in this particular case, that hydrogen cannot be, cis with respect to where the leaving group is. It has to be trans. So let's say NH2 minus, so that would have two lone pair. Just come around, strip this hydrogen off. Everything's going to happen in concert here. Just this cascade of electrons is going to come down to form that triple bond and boot off that leaving group. So then you're going to form an alkyne, right? So it's going to be a linear construct as opposed to a trigonal planar starting material. Okay, so two equivalents of base to remove this. Let's say dihalide, a 1-2 relationship, right? So each one of these hydrogens is going to be essentially acidic, right? Because you have two bromo groups that are pulling electron density away from those hydrogens. So in other words, you're going to form an excess. Now, if you would form this kind of alkyne. If you wanted to form a terminal alkyne, you would use 3 equivalents and then follow it up with some kind of acid. So just bear in mind, terminal requires 3 equivalents, base, then acid, workup. Reason being is that third equivalent that is in there is going to pluck that last proton off. Remember, it's going to, there's so much of it that's actually going to favor water formation and a little bit of that stabilized anion. Okay, last thing on the list, and then we'll do one synthesis experiment, and you can turn this off and enjoy your day. How about that? Let's look at how Hoffman elimination or anti-Zaitsev product formation. This is taking a less stable alkene. This is a vinylic product from an amine adjacent to a terminal methyl. So in other words, right here, this is, say, 2-aminobutane. So butane 2-amine, whatever. So let's say this lone pair attacks. So this is a very powerful electrophile. So in other words, that I- gets kicked off, great leaving group, big and bulky, right? So do that not twice, but once, twice, but thrice. And then you get a good leaving group because it's going to be quaternary. And that charge right there isn't going to want to stick around. All right, so when you also introduce that Ag2O, it's going to be an ionic compound, an oxide. So that oxide is going to be highly basic. It's going to strip off that hydrogen and force an E2 mechanism to occur. So it's going to happen lightning fast. You would use something like high heat to drive that elimination, right? And then your elimination product would be this particular vinyl group. And once this leaves, this is going to become a neutral species, which is trimethylamine. Okay, so again, everything for E2 has to be along the same plane. This is going to be really bulky, and it's going to want to leave anyway because it's going to be bumping into everything else. And that positive charge wants to be satiated. Okay, so this is what is referred to as an anti-Zaitsev product. This is just kind of classically what you're going to see. You may see some kind of example like that on the exam. Hint, hint. Okay, so one last thing to work out here. Now I just have some reaction arrows here. And I'm going to go through what a total of 1, 2, 3, 4, 5 steps to get to our product here in the end. Now, we do not see this phenyl group here. We do not see this particular secondary amine at the end, we actually see this cyclic ether. So there's been quite an adjustment that's been made to this 6-membered ring, assuming that's what we started off with. Which would be the case because we are going to add that benzyl group right here first. What we're going to do is we're going to use what kind of base to remove this hydrogen? LDA, that's right. So we would use LDA, the first step, low temp. And the second step, you would introduce a benzylating agent like benzyl bromide, which is a lacrimate, make you cry. Cry for taking organic chemistry. All right, so the second step would just involve this kinetic enolate to attack this very formidable electrophile, and in turn you would get this benzene ring that's hanging off of a methylene group that's attached now to this cyclohexanone derived ring. Okay, next transformation here, we're going to go from this ethyl group that has this amine attached to it, secondary amine, and we want to make a vinyl over here. So what we're going to do is we're going to do a Hofmann elimination. So the first step is we're going to introduce excess good electrophile. So that's going to form a quaternary amine here. We're going to use silver oxide, of course heat. Okay, and then we're going to get our Hofmann elimination product. All right, and something we haven't gone over just yet, we'll get into chapter 11 next time. We're going to use, under acidic conditions, let's say water. And again, I will go over this mechanism with you next time, but this is going to be an electrophilic addition. But it's going to be anti-Markovnikov. Oh, what does that mean? Well, this would not actually be anti-Markovnikov, so we would not use H3O as a type of addition product, because it would actually, this OH would actually not appear right at this carbon, it would appear at this carbon. So it's something to kind of make a mental footnote of. So BH3 and THF. So this is what is called hydroboration oxidation. H2O2 and AOH, and then water. Okay. Sorry if I'm all over the place here. So this is going to actually add that OH group to the least substituted carbon instead of the most substituted carbon. Okay, so then we're going to have that hydroxyl group right there. So that's another transformation. Then we're going to mildly reduce this ketone to an alcohol using NaBH4. So this is sodium borohydride, sort of like what we saw earlier with lithium aluminum hydride that I drew out for you. You're going to have that sodium that's going to be positively charged. You're going to have that BH4, or boron is going to be negatively charged. So this is going to be a hydride source, just like lithium aluminum hydride was, albeit less reactive, because this is not as polar of a bond as what you would see with lithium aluminum hydride. Okay, now this ethanol is acting as this proton source. So this hydrogen is actually going to come in right here. So in other words, this one of these hydrogens is going to attack right at that carbonyl and reduce things down just one step of reduction. So in other words, two hydrogens, one wedged onto here and one wedged onto that oxygen. Not together, separate, but the mechanism's there. You'll get into it more so in next semester when you take Organic 2. Now, all we really need to do here is, since this is an intramolecular reaction, all we need to do is use H2SO4 and some heat, and we will cyclize and have water as a byproduct and form this cyclic ether to wrap up our discussion for the day. Now, mind you, this reaction here, we have not gone over that yet. I'm just trying to slowly introduce this stuff to you over time. We're going to see that a little bit more when we start getting into synthesis and wrapping the semester up. So I just want you guys to be aware of that before we start getting into test mode. Thanks for your time. See you next time.